Okay, good morning and welcome to lecture 18. While still about 9 people are missing the class. Today we will try to complete MEP and active systems. So we close this chapter and all the material that will be subject to midterm part 3. I hope the sound is good. Let me know if there's any problem. So in previous sessions, we completed artificial light, mechanical systems, and today we'll have a very fast overview of plumbing, electrical, conveyance, and safety. Before that, as you know, we had a survey to decide the date of midterm part 3. I closed the enquete 15 minutes ago, and here are the results. So in total, 25 people participated, which is a bit less than 50% of the class, but the results are very clear. This is about 15 people, which is added for the majority, but still 60% prefers to have the latest day. If we add to the 12% that any time is okay, you have 72% of the participants agreeing with it. So let's fix it. Midterm part 3 will be after 2 weeks, right? So May 28th, say 10:30 a.m. As usual, it will be about 30 minutes, 20 questions, but I still have to fabricate the exam. So you'll have news notices. As usual, check Blackboard. To have the latest news, right? So that's one thing today. The second is the assignment. As every Friday, we will spend a bit more time explaining. So we already finished 2.0 and 2.1. 2.1 late submission was closed yesterday. So if anybody submits later, it's okay, but it will be the super late submission. Second part, envelope will be next Thursday. As usual, you have 1 week as a margin, but as usual, try to submit on time. The assignment is mostly working in section. So depending on the building scale, we need a general section, right? Telling at least the typical floor, connection to ground, this is the ground, connection to roof, just to have the reference. This is for context, right? Then at least 1 floor minimum, floor to ceiling 1 to 50 scale. If your building is small, it may make sense to make the full facade, right? Not only 1 floor. And then from that 1 to 50 larger design, you may produce details 120 to 125, right? So this is like the sequence of scales, which are basic. So coming from 1 to 100 to give details 1 to 5, 1 to 20 doesn't make much sense because that we don't have context, right? And optional material schedule for facade and roof, but you have examples and so on. I promised last week to show one schoolwork of last well, not last. It was my third year for Studio One and the first course of construction, right? So it's not perfect, but it will give you an idea of what is the process of envelope detailing process. And we will give a few minutes for people to complete before details. So it is almost 40 years ago. Let me change the screen because that will not be in the handout. So now I have to change the screen, which will be this one. It will be very fast. I hope. Okay, you can see. So this is actually 1982, not 1983. Let me have the full screen. So this is just a Studio One, right? So this is a rural area. We have a channel, existing channel of water with a detour to have a water mill. And there's a set of rural houses on one side. On the right side is a small school. I cannot let people in when I am now, so John has to wait. So the work was one of the units of the houses. This is the detail of that area and one of the houses which was detailed. Right. There's actually final presentation drawing. It is hand drawing, so this is why the image is not very clean. So there's a lot of research. This was meant to be built in Adobe, like a clay construction. And I had to go to books and magazines to get the details and the ways of construction. This is all research. Then you have to work the details. So this is sketching, and these actually are the corrections in class. So this is my teacher's comments. Let's change to another color. His comments on the structure and things I should be careful about. Then, well, this is the first stage, the initial design, which was a very simple house. And again, the teacher notes telling that Adobe did not make sense being unprotected because it would melt with water. So I should use eaves to protect it. So that is supposed changing, and some comments on connections and so on. So that's supposed to change in the design and to have even on the west side, which is the dominant wind with the rain, have like double protection. So the chances of touching the water, the building were smaller. The project was redeveloped at 1:100 scale, the small house. And well, so for this practice, and this is the presentation, it's like 12 sheets. This is handwritten, telling the motivation, the use of Adobe, the use of Timber, Adobe Timber, and my conclusions of the project. So you have the information, right? The floor plans with dimensions and the reinforcements for the openings, individual independent walls for the wet rooms, right? And of course the roof plans and basic annotations. Same with the sections and elevations. So this is actually only 2 elevations there. And then foundation. Well, you see that the dimensions were already in the there was a message there. We have 2 people waiting in the gate, but I have to finish this sharing screen. So the images were already in the initial drawings, information drawings. Here is all the study of those Adobe pieces. So Adobe you make on site. And the first thing was deciding the size, which you can do, which was just a 20, 10, 15 centimeters. And then give the thickness for the general enclosure and the ground floor and the upper floor load-bearing walls and the connections, how they worked. This is what you explain in the project. Then you have the full section. This is already 1 to 20, the full building, in which you have the main organization. And then with numbers, you have the explanation of what is what. And there's actually a structure, envelope, interior, and basic systems. Right? You have a chimney to heat the whole house, all chimney inside the volume, so that all the heat will remain inside, and the stair around the chimney. The long section, again, showing the construction. You're familiar already, the ventilation of the lower part, the implementation of the systems, the design of the doors and the windows, which is a kind of reinforcement in concrete to protect the Adobe, but also to have some opening in a large, very thick wall. And then, well, this was very small, so there were just the details 1 to 5 scale, right? Connection to the ground, of course, the cutting sheet is a flexible joint between brick and timber, implementation of systems, and the description of each of the materials used. Same for the windows. You may see that the window is reasonable, but it's not very sophisticated. But again, this is kind of trying to solve the connection of different systems and the timber with concrete, right? The concrete was tying all the walls, and also the support of those brick walls over the timber and so on. So something is not working perfectly, and I would change many things there, but this was just the first try. It was not easier. The connection of the chimney with the roof, which was difficult. This is quite reasonable and carefully done, but of course you will notice that this is a bit narrow, right? So it should have been at least in this thick. And then the joints of wooden structural elements and the tricks to avoid touching the chimney, which is a bit too hot, and the wood should not be in contact. The way to use thin wood elements over very thick Adobe walls. The connection of the roof elements with the Adobe wall, with this kind of a tie beam on concrete, and then a dormant in timber to have all the timber to timber connections. And we are almost finished. The design of the gable, these are all 1 to 10 scale. And finally, the eave. And this is interesting because I try to show the process, right? This is very illustrative, and how to make from the tie beam to the structural elements of the eave and the connection with the rest of the Adobe, and how the timber is protected so it doesn't get the wet, the humidity from the wall. So that's an example on how you can go from basic, very schematic design to detailing in a small building, right? And it's very clear that a sequence of scales, and you have all the possibilities like floor plans, sections, wider details, and axonometrics with the process to show the assembly. Okay, so much for sharing here. Let me go back to the further screen. We spent like 5 minutes more than I expected. So let me go back to the presentation. So this is what we saw. Let's let people in. Okay. Yes, welcome. I think there's nobody else waiting. So this is the perfect opportunity to make the initial test. Bonjin was lucky because we didn't start yet. So let's see how you're doing. Okay, please don't get distracted because the test will be closed soon. Okay, almost everybody finished, and we have to close. Almost closed. Okay, now it is closed. Okay, so let's go straight into the lecture. Plumbing is basic about water and sewage. You can include gas and so on, but it's mostly fluids conductions. What am I doing? Okay. So for the drawings, I just collected a set of symbols most used in general. They're quite universal. I have English and Korean, so it's quite convenient. Since it is abstract, I added a few slides telling what is what, right? So the ones we use more are the pole, valve, and tap. It is very reliable, just mostly just to open and close. This is what you will see often in industrial applications, garden, and so on. The globe valve is the most usual tap we use in general in houses, right? That allows for a more continuous regulation of the water flow. And well, you have the strainer, which is a filter. So this is the secret strainer, and this is the strainer which is in the symbols. And the flexible joints we commented already when we spoke of the sound. Expansion elbows, which are interesting. Just an elbow allows the installation to expand and contract, especially important in hot water, but you will want to have it also absorb some kind of a vibration. And the flanges, which are just connections, right? In Spanish, it's brida. Probably in Mexico is the same. So more interesting for us, this is a very generic diagram, symbolic diagram, and a bit more on a scale diagram for a apartment building, right? So you have the description of each element. We have to start from the city supply. And the city supply, we have to make a connection, kind of connection box. And you see there are two valves always. In those elements, we have connections or counters, and so on. We always put two valves, so we can close both sides and replace and repair those elements. So there are three cases. The street or the city water supply has already one pressure, right? So the lower floors or probably may have too much pressure. So you have a pressure reduction valve. So they have not much pressure. And then what we called before the control on non-return check valve, right? Non-return, which avoids the water going down by gravity. So when you have a very long, very high pipe, you usually put that. It's very, very simple. And then you have one distribution for the lower floors. And always you have some valve to cut that line in case you need some kind of repair. And then you have another valve which gives the access to each house and the counter if they are in each floor. If the pressure is okay, you can avoid the reduction, and that will serve usually the middle floors. And for the upper floors, you may need more, so that will make the need of the pump, right? Pumps are complex. You need a tank, so the pump can just push the water from there, and that will serve the top floors, right? And this is the diagram how it works. The connection to the city, the first connection box, the two valves with the general counter, and then the three sets, right? With the tank to bring to the pump and to supply the water to each of the floors. You see that we need usually a shaft to bring those pipes. This is very economical because you need very few pipes. And we have a message on the chat. Yeah, so the pressure reduction or the pump, usually you have to speak to the engineers or to the city, so you will know the pressure they provide, right? Usually, if it is about 3 kilograms per square centimeter, this will be like an adequate pressure, right? It's over that, you will need to reduce. If it is lower, you will need pumps. In Madrid, for example, water supply is limited. It's a dry city. So by law, all houses need a pump system, right? Use it or not. Okay. Let's continue. So it's the pump system. One more practical system is the also the three difference depending on the pressure, but you have all the counters in a room, right, in a mechanical room. So from the counter, you have just one line for each apartment of each unit. So you have a bigger shaft, but you don't need to go to each house to see the counter. And you have always the valves just apart from the counter, and then a new valve at the entrance of the house. See how also it's nice to have a valve at the entrance of each room. So you may cut the kitchen and still use the bathroom. And you should have also a valve before each of the machines. So if you need to repair the sink, you can still use the rest of the appliances. And these valves are usually the ones of spherical, the ball valves. Usually for this shaft, you calculate about 10 by 10 centimeters per tube, right? And in plan, you will try to have all the tubes belonging to one floor plan to be on the front and the rest to be on the back, right? So this is for 3 floors, and it will be like 60 centimeters by 30 centimeters minimum, and it will work. You have the space for the pipes and the insulation. That's in the case of apartments. If the units are larger hotels, you may need a different dimensioning, right? So in vertical, as you see, you will have each pipe just appearing just on the front of the shaft, so you can just inspect or repair from that inspection wall. You have a basic dimensioning for the pumps depending on the area, right? You see that the buildings are quite large, but actually 3x4 will serve most of the buildings. And then for fire depends on the regulations also, and you will need much more space, right? Usually in general. This is an example of a public toilet. So it is very practical to have a shaft to have all elements inside, which you can inspect. This is an example. Please, when you make your building, design your own shaft. I have the same we saw with the suspended ceiling yesterday. I have seen this bathroom already 1,000 times, no matter which project it is. Just one example. Just try to adapt to your own project. And then we have the sewage, which usually is in parallel. And we usually will collect bathrooms, kitchens by separate. We need a shaft. And in this case, usually we share the sewage pipe. This is symbolic, again, at the same scale. Important, you need one connection, kind of small well that you can register in each of the connections. And we have a final also manhole, which makes the connection of the building sewage to the city. That is the connection element. So in reality, you have to know on the street where the city sewage is, the depth, right, and the distance, because you have to excavate, make the connection, and have some element you can register. Usually it is in the border of the building and inside your property. So usually this well belongs to the building itself, right? There is one interesting element which you will see. Let's erase everything. You see that the vertical pipes have this dotted line in parallel, connected every other floor. Same for the kitchens, and they connect again, and then they go to the top. So those pipes have a ventilation, right? And you have a parallel element which helps that ventilation. That's important. And this ventilation is usually very smelly. It goes to the sewage. So you have to make it far away or protected from other ventilations which will bring the air to the rooms, to the houses, right? Especially if you have mechanical ventilation. This is a first question that you have to think now in 1 minute. So what is the need of this ventilation of this secondary pipe? Now, think 1 minute. What do you think we need it? And that completion I have in one pipe in parallel. Actually, vertical pipes are between 10 and 15 centimeters in diameter. The parallel depends on the height. So it should be at least 35 millimeters. Can be the same diameter, but depending on the height, you make it bigger or smaller. Right? There's a question about shaft. Yes, so a shaft is a vertical open space through the building, right? So it's like a vertical, say like a narrow well. That's shaft. And inside you may have pipes or electricity wires or sewage, right? Or even elevators, right? Usually you don't share, but yes, that is vertical corridor, let's say. And usually it is for systems, right? Okay, shaft. That's the meaning. So the reply to this is we need it for avoiding when you have a discharge that creates a void which will suck the water of other upper levels, right? And we have more difficulty going down because it creates a void. So you need to make sure atmospheric pressure will help the air going down, the water, and it will not just suck the water traps of the upper floors. The larger the building, the more important it is. And usually the secondary is used over 8 floors, right? And they always, even for only 1 floor, we put the ventilation to the roof so the water will not suck. This is an example of what is done. So toilets have a water trap top with the smell, and they may go horizontally or vertically through the floor. This is the general use nowadays. It creates a conflict with the lower neighbors, but makes much more easy repair and maintenance. You see connections always in V, right? And again, each of the appliances may go to a shared water trap under the floor. This is the same case we saw on the lower part, or over the floor, with the inconvenience of having more difficult repair. So in general, the trend is doing things under the floor. And different designs of water traps, you will try to have as much margin as possible, because when you don't use them, the water evaporates and you have a bad smell. That happens in the toilets. If you go for a holiday in a dry season, say 2-3 weeks, you may have a terrible smell in the bathroom, and that happens because that water trap has dried. And that happens a lot of in terraces, in roofs, so you have to pour water from time to time. And plumbing laboratory, so there's a lot of research going on. We cannot explain here. So you can see one toilet with horizontal, just to check the distances, the diameters, and so on, right? So to see how it works, and it's transparent, so you see what happens. Only one comment from this site. I studied, and I was told that in the sewage, especially those long elements, the diameter bigger, better, top it clogs. But experimentally, the opposite is true, because if you have some kind of deposit and the diameter is very big, the water goes through and you just increase the sediments, right? Whereas if the diameter is smaller, the water pressure will actually clean it and push it. You will need, of course, some points to register, to clean, in case, to access in case of problem. But sometimes the experience gives conclusions that are counterintuitive. And I think that is the basic for the plumbing. Only one thing is the color coding. This is a construction site, apartment building, and you see a mess of cables, pipes with color codes. This is scary because many of those pipes are inside the concrete, and you see there are areas of the concrete which are almost just void pipes, and this is not calculated. So no matter how big the safety quotient is, this is a very random thing, right? And this is like going beyond that, so it should be calculated. I saw this only in Korea. In other places, in Spain for sure, you never touch the structure. You calculate solid concrete and use solid concrete. But the point is the color coding. And it depends on the countries. So for pipes, for plumbing, this is American standards. Usually very common. I usually put American standards because they are the inspiration for Korea. Usually fire protection equipment is red. Green is general water. Actually, light blue or just blue is the drinking water. So that's a bit ambiguous. And yellow is usually flammable, but usually it's just for gas, right? And there's another standard from painters with a bit more detailed standard, which you may want to refer to it. So if we go to, again, Renzo Piano Katie Tower, we see clearly the fire pipes and the other fluids, which in this case may be, I'm not sure what, probably some kind of a refrigerating fluid or so on. Let's go to electricity. This is a famous photo of Tesla in his experiments in his laboratory. So the same as it happens with plumbing, we need to have the city supply. And we have 4 cases, actually 3 cases. Very small buildings, say individual house or small villa with no more than 5 or 10 units, you may have just the direct connection, the transformers in the city, and you have your meter, and you have the low voltage straight into the house, right? You have your meter, and then the control panel, and then each of the circuits, which goes to the rooms. Medium-sized buildings, and that means probably more than 10 units of housing, depends on the companies and the size of the buildings. That's my experience. You will have medium voltage. Medium voltage is between 1,000 and 30,000 kilowatts or watts, right? So like about 100 times more than the usual. You have a high tension meter for the whole set of for the whole building, say. You have an outdoor transformer, or preferably a room with the transformer and all the general switches and safety equipment. And then you have, as we have with the plumbing, one line to each of the units. So you have all the counters, and at the entrance of each unit, you have the control box, right? And in very large buildings, you will need like a really huge transformer and a different room. If you want a reference, in Spain, for example, I have to make the transformer volt for just 25 units of large apartments or so on, included the parking also and garden, right? There's one thing I want to comment, because the electric power is alternate, right? Sinusoidal, and it comes in 3 phases. And people are often confused with it. Sorry if you know already, but there's many questions about it. So usually the electricity is generated by a rotation element with a system of magnets, right? Which will create this kind of induction electricity, which you collect. And the 3 magnets will produce electricity 3 times. So you have the first one, the second one, and the third one, right? And they have a difference of 60 degrees each, I think. That makes, no, this is 360 divided by 3. So it's 120 degrees each, right? 120 degrees, it is written there. So that means we have 3 lines of electricity. Each line comes from a different phase from the generator, right? And the fourth one is the neutral. So those will switch plus minus, plus minus, plus minus. And this is the neutral without the power, which will give us that difference of power. Right? In continuous power or direct power, DC, direct current, you have always plus and minus. And plus is the one which is the power and which hurts when you touch it. The minus is just receiving the electrons, right? So you don't have any touch. So that's the case of the neutral here. And again, the standards are different according to countries. So probably Korea uses US standard. You have to recognize always the neutral, which is the non-dangerous, the one who has not power on it. And the green or green and yellow, which is quite international for the grounding, right? So Europe uses always green and yellow, but you see green and you know it's the grounding. It's important cable. But this is tricky because others, maybe black, brown, red, orange, and so on. But those two you have to recognize so you know what you are touching. In Europe, for example, and this is the difference, the earthing is universal, but neutral is blue. Now we use black, brown, or gray for the faces, for the different faces. So that enters in conflict with the American standards. Probably Mexico follows also the American system, I guess. So for me, it's very easy. When I do something, I know blue is neutral. So I know that's the safe cable. So usually in small houses, you would have only one phase, right? 3 phases are used for machines, big air-conditioned elements, elevators, and so they need all 3 phases. And the counter is different, and usually the contract is different. If you have a house, usually use only one phase, and that goes around. But if you have a large house with 3 phases, you have to divide those 3 phases so the power is shared, is divided or distributed with some kind of regularity. So you have, again, dimensions for transformers and larger volts and switch rooms depending on the size of the building, right? And usually you see even small buildings, 1,700 square meters can be an individual house, right? You will go already to a small room there. The rooms have not much mystery. Can be a kind of a closet or just a room, right? You need always a space to move around and the space to have all the counters. The tables before will give you the basics, but usually will never go below 1.5 meters, right? And when you make a room, you need the space to move around. The advantage of the rooms is that you can also put switches on the walls. And the distribution system is quite straightforward. It's easier than plumbing because electrical wires need less care than water. The common case nowadays is to have the main switch, then the counters room, and then one line per each unit. So you have a shaft with the cables. This is the scale drawing, right? So you will have each cable going directly to each unit. And you have the switch room, and then you have lines and connection boxes and so on. You have some basic dimensions. If you want to have a bit more detail, we don't have time for that. One thing which is important, we need always one counter for the common spaces, right, which are shared. So elevator, stairs, and so on. And probably you need a different for the parking, because often parking users are not the same as the units users. So in some cases, you put different counters, so the cost will be shared by the real users only. And this is the example of the shaft with all the individual cables for each of the elements. See how the elevator is 3-phasic, so it has the 3 cables going there, plus neutral. In this case, for the shaft, the system is the same. You may count about 10 by 10 centimeters per line, and you are more or less in dimension, right? And when you go to ceiling, we commented yesterday that electricity should be over water. In this case, the electrician arrived late, and you have the fire line over the electricity. This is not a drama. I don't think it's forbidden, but it goes against the general rule of avoiding any risk of the water leaking over those lines, especially those connection boxes. Usually we make them waterproof. You can have them even in exteriors, but in practical life, when we have problems of short circuits, the first thing we look about is those boxes in exterior, because sometimes they fail and you get water inside and the electricity becomes a small disaster. That may happen more rarely, but may happen in interiors. So why would you want to take a risk on that sense? In offices, it is common to have it under the raised floor. In this case, the difficulty is in deciding the modulation depending on the use, right? You don't have it always right. That needs to have a big communication with the client, or very good knowledge on all the possibilities of the office space use. This is also KT building in KUA. Let's go into conveyance, right? You see, we cannot go with much more detail, but I hope all those diagrams and the numbers are practical. So you can just implement that and have them into account in your project. So conveyance is mostly elevators, also escalators. Very few times you will use escalators. Escalators are very energy consuming and very expensive, but in large affluence of people, they make sense. So department stores, subway, and so on. Sometimes we design escalators in public spaces and they end abandoned because people do not use so much, and maintenance and power is very expensive. And often they get abandoned or just closed or stood. So the photo is Otis, his demonstration of the safe elevator. The moment he demonstrated you can cut a cable and you don't fall down, became actually one of the factors to start the skyscraper and the construction in height trend, right? So again, elevators, we have two main families, mechanical versus hydraulic. Hydraulic elevators have a hydraulic system, just a kind of oil by pressure. It really has a piston, so it's like pipes which are pushed by that fluid, and that makes the elevator going up and down, right? Hydraulic lift or elevators may have this element in any floor. Usually it's the lower part when you push, but could be anywhere in the building. So it is very flexible, and you don't need top machine room, right? They are very slow. They are cheap. It's simple, but they consume a lot of energy. So usually in small buildings, actually they have also a limitation because of the system. The pistons cannot go up forever. They are solid elements, and that's an inconvenience. But they are extremely powerful. So for very large loads, they are excellent and very reliable. But they are painfully slow, right? They can be they can take like a 3, 4, 5 times as much the time to go from one floor to the other. Traction lift is the usual. It is a mechanical electrical motor, which is usually in the top, in the roof, which is working with cables. So this is a bit more expensive, but it's faster and can go to long distance, right? And this is the general case. Because lift is British for elevator. So this is the summary. Mechanical is the general, right? It's also called traction. It's fast, can go long distances. They are more optimized for energy consumption. They're expensive in general. The loads, also we have a very powerful elevators, but usually load is a weak point. They are more complex. They need more maintenance. And in general, they need a large machine room, which means more square meters, but also one more stair, right? Flight. It means structure, interior, and envelope, and so on. So that adds to the price, which you save. Hydraulic are painfully slow. The distance is usually that I know limited to about 5 floors. You cannot go much more. They use more energy. Also, they are cheaper and very simple to maintain. And they're excellent for large loads. So most of the parkings, right, this is usually 1, 2, 3 floors you go down, so you can have time to wait. And you can have cars, trucks, buses, tractors, large loads, right? And the machine room can be on bottom, can be in any floor, but usually it's bottom, and you need very, very few small space. So that also saves additional money. And as I said, most car lifts, and that may apply also for large cars, are hydraulic. If you have experience, you'll notice they are quite slow, right? That's not because of the load, it's because of the limitations of the system. I brought some drawings in case you use them. You see, in this case for cars, they give you 4 floors of difference. On elevators, because I saw in your drawings you are a bit confused, you need always a pit, usually 1.1 to 1.5 or 1.6 meters, depends on the elevator, and overhead, which is about the same, 1.1 to 1.6, which is just for safety. You have people working inside, they can just crawl in case of the elevator coming up and down, and you don't get crashed. Right? So you have a small margin for the movement of the elevator. So you have plan and section. This is a basic pre-dimensioning for elevator shafts, depending on the shaft of the building, and basic elevator dimensions. This is good for pre-dimensioning, but my advice is to go to the web of elevator makers, right? Most international makers have joint ventures with Korean companies. So Schindler, Otis, Kone, you have always the second family name with some Korean companies. So you will find the real elements which are sold in the market. This is the basic general system, right? You can share the shaft, but you need some separation between cars or cabins. You need a pit, and of course overhead space always for the safety we said, and space for the machine room, right? Depends on the makers. Counterweight is important. So the counterweight is 50% of the maximum weight. That means that when the elevator is full, you will only move 50% of the weight. When it's empty, you will move maximum 50% of the weight. So it's quite an ingenious system to always reduce effort. And something which is interesting also is the dimension for double doors. They can be in the corners or opposite, or it can be simple, right? 800 is the minimum for accessibility. Be careful because some codes will ask for 900. Just look at the basic minimum cabin for a wheelchair. It will depend on the codes. And something which has been around for over 20 years, I would say like 30 years or so, is elevator without machine room. I didn't see yet in Korea, but there's so much experience that makers are able to put all the machinery inside the shaft. So you have the shaft, you have the elevator cabin, and the whole machinery can be just on one side, and you have only one opening for servicing it. Of course, you can also access from the shaft if you need. And that saves one floor. They are very optimized. They were very expensive in the beginning, but nowadays, I would say since 20 years, I didn't use anything else that elevators without machine room. They're great. And when I checked one of the makers, KONE was the one which patented first the system. They can go up to 63 floors or 180 meters. You have here the dimensions if you want to see them, and the reference to the web. And then the sections, again, with the shaft and the overhead. Escalators are pretty standard, curiously. So you have like the 82 and 120 centimeters escalators. You may find order-made elements, and in general are 30 degrees. And knowing that may help you design stairs. So 30 degrees is also quite convenient or comfortable stair, right? Standard stairs are a bit more steepy, but if you have the same angle, the set of elevators and stairs will look much better. Let's go into safety, which is the last part. And it is not formally included as part of the requirements of our course, but as we commented, a studio of fourth year, fifth year have safety, and safety is one of the SPCs we fail inspection after inspection. And it is a serious matter. And mostly fire safety has to do very much with design. And one thing which prevents us from taking it seriously is our perception of danger. Do you know how many fire disasters happen really in a city? Not the ones you see, but the ones which happen in reality. Well, if you look into the statistics of Seoul, well, last time I checked this was 2016, they had almost 6,500 fires only in Seoul. That is almost 2 fires per day. This one photo of one fire I randomly saw when I lived in a tall apartment. I would see smoke going around every so often, right? The fire service in Seoul is excellent, so most of them are okay, but we know eventually they are really, really big disasters, right? We have one fire in Namyeonju a few weeks ago in a multi-use building. Of course, bad design, bad use, bad maintenance, and those guys have been out of the house for weeks. So the point is that fire protection is basically designed to save lives. We give up on the building. So if the building has to be demolished, we just accept it, but we try to save lives, right? In general, we will see exceptions to that. And to save lives, we concentrate on the escape, the possibility to escape from the building, what we call egress or escape. This is very generic, depends very much on the standards. You have to study the standards, and the fire standards change all the time. in 30 years, I have been, well, many more than 30 years, 35 years, I have been working in Spain. I have been already over 6, 7 different standards, every time much more strict. But usually you need at least one fire emergency elevator. This is Korean. At least one stair, right? And the maximum 30 meters from any escape point. If you have sprinkles, you may have 50 meters. And this is in Korea, depends on the codes, but underground floors need 2 stairs, right? The stair needs at least 2 hours, depends on the size of the building. So you have time to escape, and the firemen have time to go up in the time the building will stand. Remember that in the structure we saw that we have 1, 2, and 3 hours stability. So if we want the building to be 3 hours standing, we would need at least 3 hours of safety in the escapes, right? In the escapeways. And of course, we need to make them smoke proof. There's no use to have a fire escape if it is full of smoke and you die while you run out. And this is done by double doors, by natural ventilation, or by pressure, and so on. And the dimensions depends on the occupancy. We cannot go to so much detail. You'll have to check the codes for the dimension. But usually the general corridor size of 2 meters for public buildings or 1.2 meters for houses, so it will work in most cases, but still you have to check for occupancy. The concepts, you have rooms, usually the escape origin is the gate of the room, right? Unless it is an open plan office, a department store, then it's open plan, you have to consider the farthest point, but usually escape is from the exit. Usually those doors are fire resistant or smoke resistant. And then you measure the distance from that exit to the stair space. And this is the 30 meters or the 50 meters we commented before, right? Then if the stair is safe, the rest of the distance is not taken into account. And usually the exit goes to a safe space, right? Public way. But I stress safe space because in Seoul we have many alleys which cannot be accessed by firemen, and sometimes you will have difficulties to have them accepted as safety or safe exits for the building. And in general, we try to have this space between the stair and the building to be also safe, right? To have a resistance to fire, at the same time to have ventilation, and not to have any kind of dangerous spaces. You have a restaurant kitchen next to it, and you have a fire in the restaurant kitchen, right? You cannot exit the building anymore. So you have to make sure that exit is safe. This is the sprinklers. This again, KT building, very useful. And you see the provision of the openings, so you don't need to use too much space. But we have the fire protection of the structure, and then the interior mechanical engineers start scratching that protection, and I don't think that's very correct, right? Because, well, there's a small leak, but that may be the start of a disaster when you have a fire. When you have 2 distances, you will try to have them as far as possible, so the possibilities of them being blocked is minimum. Same with the corridors, you have corridors around, right? So you will try always to have as much more independence. So if there's a fire, one of the alternatives will be always free. Exterior corridors are great because they have always air and give much protection. So that stair is very unlikely to be affected for the fire of any unit. But that means that all the doors should have some kind of fire resistance. You have to avoid as much as possible dead end corridors, right? If you have them, you need to have very clear signaling, so it doesn't happen as it happened in Seoul last year. which people got lost and couldn't find the exit because they didn't see the signs. So they just suffocated under the smoke. Then this is the basic distance we commented before. We don't need to insist. Only when we have this kind of open office space or larger spaces, you may be required to consider the space from the room. But usually we consider the exit of the unit. For apartments and hotels, usually it's the room, right? In offices, it depends on the size and the codes, of course. This again, the division of the building in areas for safety, right? So you will be able to use any of the exits in any way. And I think it's very important because it depends much on the design. You will try to avoid the doors blocking the space and even blocking the circulation. So even though this is accepted, I would choose always the case of the doors not invading at all the escape space. And those I mark with a triangle, I think they are okay in the States. In Korea, they are forbidden, for example, in most of Europe. If you have to escape this way and people open this door, you may end up crashing in the opposite. If you open the other way, right, and people are running in this direction, you may not be able to open the door. The same in the stairs, right? So that opening is always a danger and people escaping. And there is also the use of the building. This is important. Fire door should be always stopped or closed, or should close automatically in case of fire. But this happens all around Korea. Right, happens all around Korea. And there's the fireman inspection. They clean everything, and the day after, it becomes a disaster. If there's a fire in this floor, all the upper floors of this building are done. They cannot escape. And even if the doors close, you have obstacles on the escape, and this is a source of injuries and so on. And this happens in apartments, department stores, in offices, in which stairs become storage space. Okay, so passageways is the concept of having a safe space to shorten the distance to the stair, right? In general, they are safe, but the weak point are the rooms which access to this passageway. So you need to have a very, very safe enclosure there. So this escape is not compromised. So it has a weak point. That happens the same, especially in this chart, the escape floor. The accessibility issues, we have not a solution for accessible fire escape. In that case, the fire elevator is the ideal, but fire elevators for the occasional disabled user may be okay. But if you have a building, say a hospital, school of disabled people, they will need a lot of time to evacuate the building. In the case of the stairs, it's quite desespering because they give you a waiting space. So you have this 1 or 2 hours and hope for the firemen to rescue to be on time and to take you out of the building. This is better than nothing, and this is why we need a lot of extra space. But imagine yourself in the skin of a disabled people depending on the wheelchair, waiting on the stair, while everybody else is running their way out. So it's not great. This is what happens in Chancel Tower, right? You have like a safe spaces, and while you hope your risk good. Yeah, the lifeboats, what they called. Well, I hope no fire hazard happens. Ventilation is important. The easiest is to have natural ventilation, right? That's great. Otherwise, you have shafts. Usually shafts if you have each of the floors, you will need, let's say, 2 shafts, or one on each side, right? One which gives you fresh air, and other which collects to the roof. So one is connected to the ground floor, another to the roof. So you have always some air movement by stacking. At least this is how we do in Spain. Otherwise, you have a mechanical shaft. Mechanical shaft just puts pressure into the room, so the smoke will not enter in, will be always pushed out. Mechanical is great. It's the one used in large, complex buildings, but in case of fire, you may have electrical failure. So you depend on electricity. Nothing is perfect. This is the perfect design of the stair. Look at the extension of the handrails and the way they are done, so they do not conflict with people escaping. So it's perfect stair design. I see in Korea very often very narrow platforms, and that becomes a bottleneck. And actually, this will be the real width of the stair. So this is totally forbidden. What could be accepted is to have this circular, right? Most codes admit it because people actually go in rounds. And finally, discharge. The point of discharge is to have a safe space, right? The best is to have the stair direct to the street, and if you have a vestibule or something like that, as we said, you need a very safe door, a very safe space, so you will not have the exit compromised. The other thing, apart from the escape, we are almost finished, is the limiting the fire expansion. So you give stability to structure. Minimum is 1 hour, can be as much as 3 hours. Fire rating of facade. Remember that we have many disasters in which the fire went through the facade. That's the Camfrel Tower in London. Camfrel, right? Camfrel. But it happened also in Seoul recently, in Busan a few years ago, right? It's the fire went to the facade. So you need some space between 1 or 3 meters between windows to be fireproof. And then we divide the building in sectors. Usually it's like 1,000 meters, very standard, and between 1 to 2 hours. And usually doors have the half the rating of the walls, right? This is why you see in department stores like curtains, which will divide the space in bits, and you have escape doors later. So we always try to limit the fire expansion that way. You have more details in the full handbook in Blackboard, general materials. And then we have active systems like alarm, smoke detectors, temperature manual, extinguishers, hoses, sprinkles, and foam, and so on. That all is in the additional materials or in the standards you may look. We have fire extinguishers. Usually we try to have, well, that's very unusual, but usually we have the mixed ABC. It's not a brand, but it means that that extinguisher will be able to handle any kind of fire, unless you're in a very specific use in which you can choose the extinguisher. The fire hoses are usually in safe spaces, so the firemen can safely access and then use them in the building. So it's in the stairs or safe corridors. This is a nice design. This is Haneda Airport in Tokyo. Can design. And this is the signage. Signage is extremely important. It's very frustrating because you may design carefully the signage and the inspector will tell you to do it in the usual way. Be careful with the redundancy because it may be confusing, and be very clear so people are not lost when they leave the building. Oh, we are already finished. So only one example. This is the Matrix of Architecture. We have a great collection of rare books. And in this case, we worry about the books. This is the Seoul National University visit, my Sonbe, Kim Kwang-hyun, and your Sonbe, Kim Hee-bom, right? And they were looking like really, really fantastic books around there, right? Like a dream for the scholar. And that is protected with alone gas, right? That alone gas extinguishes the fire automatically, but people die, right? So when you enter this deposit, you have to sign, you know the danger, you have to escape immediately, or you may not make to the exit. So sometimes the goods are more important than people. And that's the last, sorry for those 2 minutes. This is the source of most of the information. And this is the password for the final test. Thank you so much. Say goodbye when you finish. Be benevolent with those 2 minutes. No, with these 2 minutes, right? And say goodbye when you leave. I will wait for a couple of minutes so you finish it. Goodbye. Okay, almost everybody's doing it. Please do it fast because we have already 1 minute past, almost. Okay, I think a couple of students fall asleep, but we have to finish. So it's closed. See you next week. Okay, goodbye.